welcome to our presentation. We are topic 9 and we'll be going over simulations. Oh, my name is Yue. Okay, so for us, we're talking about simulations, and one of the first questions is why? Why do we use simulations? And the answer to this is because current analytical methods are sometimes not sufficient enough to analyze the complexity of the model that we're trying to analyze, and as a result, we have to take something else that is simpler to simulate and then have that represent our true distribution. And so an example of a truly random simulation is when, say, we need to generate some uniform discrete distribution from 0 to 8, so 0, 1, all the way to 7, and this gives you 8 different, values that you can have. And so for this, we can use something like a quarter toss when you have heads or tails, and you just toss it in whatever distribution, and you know that if you say you have three sequences, then you have 8 different combinations of heads or tails that you can have, right? So it could be heads, tails, tails, heads, heads, tails, and there's 8 different kinds. So you can have each of these represent one of these numbers, and this way you can truly randomly, as long as your point is unbiased, simulate some kind of discrete uniform distribution. But for our purposes, we are using the pseudo-random sequence to use simulations because this is just a lot easier to deal with. Things like Excel come with a random number generator, and so it's not truly random, but anybody who doesn't know how this sequence was generated won't know that it's not random. And so for our purposes, this is what we're going to use because this is what is mostly covered in the SOA exams. So the simulation approach, I'll write this here. Has 4 steps. So your first step is you build a model. For S, which is dependent on random variables x, y, z, etc. And so these distributions, you know their dependencies and you know how x, y, and z are distributed. From here on, we do step 2. So for j equals 0 all the way, j equals 1 all the way to n, we're going to generate pseudo-random values with whatever generator we're using that are called x1 all the way to x sub j, and then we compute s using the model from 1. So we know how s is dependent on x, y, and z. Once we generate all of these values, we can then compute what this value of s is since we know the dependencies. And from here, we can draw the CDF of s because we have these sample numbers that we have, and based on this sample, we can draw all the distributions and the charts, and we basically model it from the portions of random variables that s is dependent upon. And finally, we can compute quantities of interest, such as mean, variance, and percentiles, probability, and such like that, because we have this CDF computed. So I guess step 4 is compute. So this is basically the simulation approach, and this is covered on the SOA exam. So one of the questions here is how do we get, where is it? Here it is. How do we get the pseudo-random sequence after so we need the pseudo-random sequence to be fed into this model here. And how are we supposed to get this number when our random generator only goes from 0 to 1? Sometimes this is inclusive, sometimes it's not. Most of the time, we're not trying to simulate a uniform distribution. And so as a result, we're going to have Michelle here cover the inversion method, which is how do we get a pseudo-random sequence that is uniformly distributed from 0, 1, and get that to represent some kind of another distribution, like say Pareto or exponential. Thank you.
Hi, I'm Michelle Gregory, and I'm going to be talking about the inversion method. We mostly use the inversion method for the SOA problems. Almost all of the simulation problems on the SOA sample problems included the inversion method, so it's a very important concept. So as Yue was saying, for the inversion method, we start off with a number, or several numbers, from the uniform distribution 0 to 1. But how do we get from this distribution to whatever distribution we may be using? What we do is we take the numbers that are given from this, say 0.62 and 0.91, and we plug those into, or we set those equal to the inverse cumulative distribution function. In other words, we're generally told that these numbers come from say an exponential distribution, and then we would set those equal to the exponential distribution and solve for what our x would be. Here, this is for an exponential distribution with a mean of, say, 0.5. And then we simply solve for our x. This is a very good approach because it allows us to get the entire exponential distribution and doesn't tend to be biased towards one side or the other. I'm going to do a sample problem with the inversion method and then talk about some special cases. Okay. Say we're told that our population comes from a 2 Pareto with alpha equal to 3 and then theta equal to 10. And we were given that one of the numbers from the uniform distribution that was generated by some type of random number generator is 0.48, and they want us to figure out what number is simulated. Generally, on the SOA problems, they'll give you the number that you're from 0 to 1 that you're supposed to use, so then you can just solve for your x. So here I set 0.48 equal to the inverse cumulative distribution function. So we have 1 minus 10 over x plus 10 squared. And this formula just comes simply from the tables for the cumulative distribution function of a 2 Pareto. And then with some manipulations, you get that x equals to 3.8675. And you can see that this would fit right into a 2 Pareto distribution. Now, some special cases that might come up with the inversion method is if you have, for discrete distributions, if you have probability or cumulative probability distribution functions that are constant over some interval, you wouldn't know what exactly to set your x equal to. And what we do for these purposes is we choose the largest number in the interval. And again, this is for constant CDFs. And this really just goes back to the idea that when you have a random number generator, frequently they don't generate up to the value of 1, so they tend to be biased a little bit more towards the lower half, so you want to compensate for that. And just another note is sometimes it can be difficult to tell exactly where a number fits in for the cumulative distribution function. For a 1-to-1 distribution function, it's generally pretty easy, but for the ones that aren't 1-to-1, it can be more difficult. So what you should do then is maybe just draw out all the cumulative distribution values, and then maybe just try to draw in where the value fits, and that might be a little easier than trying to just calculate it.
All right, I'm Eric, and what I'm going to be doing here is showing you what value of n you should use for your simulations when you want to obtain an estimate with a certain degree of confidence and a certain error. So when you are doing your simulation approach, you must ask yourself what value of n should be used, and you should know that for any consistent estimator, it'll be arbitrarily close to the true value with a high probability as the sample sizes increase, and in particular, empirical estimators have that attribute. And often is the case, you can use the central limit theorem to get as close to that value as you want with a specified probability. All right, so as I have written here and will explain, you'll get that. So for a sample of size n, you have 0.95, your degree of confidence is, is equal to the probability of 0.99 mu, less than or equal to x bar n, which is less than or equal to 1.01 mu. And this is, you want your mean to be within 1% of the true value. And then, so you go ahead and standardize it, and of course you get probability of negative 0.01 mu over sigma over square root of n is less than or equal to z, because this becomes z when it's standardized, and it of course has the standard normal distribution, and that is less than or equal to 0.01 mu over sigma over square root of n. And knowing from the standard normal distribution tables, you will get that this is equal to 1.96, and then you go ahead and you solve for n, so you do all the proper manipulations, so you like 0.01 mu times square root of n is equal to 1.96 sigma, square root of n is equal to 1.96 sigma over 0.01 mu, and you end up with n is equal to 38,416 sigma squared over mu squared. And you're going to have to go ahead and estimate the values of sigma and mu with the sample standard deviation and mean. And you go ahead and do that, and your estimates will improve with n, so you're going to want to stop when n is greater than or equal to 38,416 s squared over x bar squared n. There we go.